Okay, so let's begin with some basic concepts of enthalpies, because really a lot of what we're going to have to solve is going to be based on connecting enthalpy and mass balances, and you guys are quite proficient at doing mass balances at this point in life. So let's remember a little bit of some characteristics about the mass balances of the mixtures of air and water. I'm just going to remove that. So we are going to simplify our calculations by assuming that the specific heats can be approximated with some simple quadratic functions, and that the enthalpies are just the product of that specific heat by the temperature. This is not entirely correct, because the enthalpy is truly the integral of the specific heat from the initial temperature to the final temperature. And if you have then an average specific heat properly calculated, you can do that. But it's going to give us a slightly better approximation than if we simply use an invariable specific heat. So we are doing, let's say, not the perfect calculations, but a calculation that is a little bit better. So we're going to be using values of specific heat of air that are going to have some kind of coefficients of this kind. Just some quadratic equation. And for the water vapor, we'll have something similar. So we have those coefficients, and they are defined as names in a spreadsheet. So you just use the equation, copy and paste it whenever you need it, and connect it to the temperature, etc. The inconvenience of this is that would make a lot of the equations implicit, and therefore you will have to either use solver or use a recursive iteration or some simple trick like that whenever you're going to solve equations in which these CPs are involved, because most of the time the enthalpies that we're going to define, for example, the enthalpy of the dry air involved in an operation is going to be CPA of a given temperature multiplied by that temperature, and that is fine if you have the temperature, but it's a pain in the beep, the camera is recording, if you are trying to figure out the temperature when you had the enthalpy, right? So if we have this enthalpy, you can calculate it like that. And as you remember, the enthalpy of the water vapor has to include the evaporation term, the enthalpy of vaporization of the water at 0 degrees, right? So the way we operate here is we assume we evaporate the water at 0 degrees, and once we have that vapor at 0 degrees, we start heating it up, and we calculate the amount of heat that we need to bring it from 0 degrees up to whatever temperature we are. Again, we're going to use the simplification that water vapor calculated at the temperature, we multiply by the temperature. If we were to be really accurate, we should use a function that provides the average specific heat. All right. Once we have the enthalpy of the air and the enthalpy of the water vapor in that air, these are to be combined depending on the proportion between the moisture and the air. Now it turns out that in drying or air conditioning and this sort of operations, it's traditional to refer the compositions to the dry matter. because the dry part of the air doesn't change during the process, so it's fairly convenient to refer to that. The dry air that goes in is equal to the dry air that goes out, so that's fairly convenient. So in the case of the air, or I'm going to call it air, but sometimes could be combustion gases, right? Remember, in our lab, in fact, we call that air, but it's really the combustion gases that come out from burning the propane, right? Now, the amount of CO2 there is fairly small, and we do a very minor reduction in the oxygen because we have a huge excess of air. So it's not that far from air. You could breathe that stuff if it was not at 210 degrees, no? It's probably better quality air than when you find in Beijing or someplace like that, no? But we are going to call it in general air, okay? And that, the enthalpy of that air, which is moist air, because it contains moisture, that enthalpy can then be calculated. So enthalpy of the air, you can call it HMA or some general name that you want, is calculated by including the moisture content. So we're going to call that moisture content MC. So this is moisture content. And there is two traditions in moisture contentology. Some people use it in kilograms of water per kilograms of air. Of course, there is people that even use it in pounds per water, per pound per air of air, no? But I am not in that. I don't belong to that religion. But I find it a little bit easier for me to use in grams of water because the numbers are like 10 or 20 or 5. And I find it that those numbers I can count with my fingers, so it's a bit easier. And but if you do that, then you have to be dividing and multiplying by 1,000 all the time. So be aware of that, okay? Carry that 1,000 very carefully with you. If you need to bring it to the exam, bring a bright 1,000 number that you can use every time you need, and be very conscious when you divide and when you multiply, okay? Because it's mischievous. Okay, so if we're going to use it in grams of water per kilograms of dry air, then I very strongly recommend you to always keep your units so that you don't get confused. Grams of water per kilogram of dry air. This is a letter G in an ancient type of script. This W represents water, from whence all life comes. And this is the universal sign of division, war, and other disgraces that befall upon humankind. Kilogram, kilo for 1,000 grams, the same. Dry air. So grams of water per kilogram of dry air. Per kilogram of dry air. Very important. This is a dry basis. Right. So the way we're going to combine these two, because it's per kilogram of dry air, this one will already be per kilogram of dry air. Right? Because if the specific heat is given per kilogram of dry air, right? What are the units of specific heat? Kilojoules per kilogram per degree. We multiply by temperature, right? So these units are kilojoule per kilogram per Celsius degree. If we multiply by this T, which in reality is a delta T, then we get kilojoules per kilogram. But this is dry air, so this is per kilogram of dry air. And this is per kilogram of water vapor. So we can write this as the enthalpy of the dry air plus the moisture content divided by 1,000. This division by 1,000 converts these grams into kilograms, right? Remember, you have to be careful, no? Why do I divide by 1,000? If I have 1 gram, that gram is 1,000th of a kilogram. And then you multiply by HWV, and that's it. And we use this formula lots of times. Now, as you can see, when you want to find, if you have an enthalpy and you want to find the temperature, it's a little bit uncomfortable because the T is in there in many places. So you can use solver or you can use whatever you want, no? Okay? And then you can find it. Okay? When would be a situation like that? For example, if you are adding a certain amount of heat and you want to find out where the air ends up. Or you know that you are adding heat and water. So you are changing both, you know the final enthalpy and you know the moisture content, things like that, no? Okay, so this is going to be an important piece of work that we're going to find many times when dealing with the air. Okay? And always remember to calculate the enthalpy considering the specific heats as they are affected by temperature, because they change considerably in the ranges of temperatures that we do. Especially the water vapor is multiplied by the moisture content, and then the air changes a bit, right? So drying goes up to 200 and something degrees, and then the air changes quite a bit. And then the moisture content has a considerable effect on the enthalpy as well. All right. So that's how we deal with the enthalpy of air. Yes?
So could you go over again how you got CP water vapor?
So the